Hi, I'd like to talk a little bit about sampling distributions. Seems that this is an area that's gotten really tough for many students to understand. So if you already understand all about sampling distributions, the distribution of X bar, how does the mean look when you have a bunch of samples, then you probably don't want to watch this video. I have a feeling I may get kind of long on this. This is a site I found online, and I will include the link so you can play too. Here we have a population. All right, it looks pretty normal, doesn't it? It's got a mean of 16, median of 16. Oh yeah, they're both the same point right in the middle. Standard deviation of 5. So yeah, nice normal distribution. So let's do a sample of size 5. All right. So I'm going to say, take 5. Boom, 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 boom. There we go. We got 5 data points randomly selected, and the mean of those 5 is right here. Not too bad, right? Okay, this guy's kind of far from the middle, but hey, it kind of balances out. Well, let's try that again. Do, 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 do. And oh my gosh, we got the same twice in a row. Now that's pretty unusual, so I better try this a few more times. Dun, 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 dun. So we keep getting a sample size 5, and from that we get our distribution of X bar. Notice each time we get 5. Dun, dun, dun. Then we get a new data point for our distribution. So these are X bar down here. This is the individual X's, and again, the parent population. Well, I could keep doing this, but it's going to take a while because theory says we need an incredibly large number of samples. Actually, they say all possible. So how about we do 10,000? Boom. Oh, don't get to watch the animation, but still, we're getting where we want to be. So let's see here. The mean is 15.97. Pretty close, isn't it? Remember that the mu of X bar, the mean of all sample means, is exactly equal to population. Well, again, 10,000 is a big number, but that's not all possible. Now, standard deviation, instead of being 5, is about 2.28. Well, shoot, I can't do this in the air, but the system says we're supposed to say, well, the formula says we're supposed to take the standard deviation of the population and divide by the square root of n. So what's 5 divided by the square root of 5? Well, I don't know. 2.28 doesn't sound too bad. All right, just for grins, let's go 100,000. Aha! 15.99 compared to 16. So look at that. Yeah, we center on the population mean, but the standard deviation is smaller because when you saw those 5 data points, while they were spread out about the mean. Okay, well, big deal. You got a normal population, you get a normal distribution of the samples. So let's see here if I can start messing with this darn thing. All right, I'm just kind of playing around, trying to make something that does not look at all normal. Uh-oh, I'm going to clear, because I'm going to start over. I guess that's not too bad a mean. See, the trouble with trying to make up a distribution is, all right, so what's happening there? But notice now that the mean and the median are not the same because this is not a symmetric distribution. I guess I'd say it's skewed, but I just threw this stuff out on the far end just to make it look less normal. I'm just playing around, sorry, bear with me. Trying to get Well, I was trying to get 10.5 for mean, but I can't quite do it. All right, so here we go again. Let's take some and oh yeah, we're gonna get a lot more over here and some over there. That wasn't too bad. And if we take these 5 numbers and find the average, boom, we're right there. Okay, so we're not doing too bad. Do it again. Ooh, wow, very different, isn't it? Again, 5 data points, and there is the distribution. Sorry about that. All right, here we go again. Another one. And another one. Getting the hang of this. We're taking a sample of size 5, and then we calculate X bar, the mean of that sample of 5, and we put it down here on this chart. All right, well, okay. Let's do 1 or 2 more. Everybody with me? I guess if not, you'll have to just watch it again or figure it out on your own. So, boy, they seem kind of spread out, don't they? Let's see what happens when we do 10,000 of them. The mean is getting pretty close to the mean, even though we've got such a weird distribution. Not exactly what I'd call normal. It's kind of off a little bit. Standard deviation is smaller again. So remember, those 2 formulas don't really say you have to have a normal distribution. They just say, oh, here's how it's going. So, I don't know, let's try 100,000. Okay, so doesn't look like we're going to get a normal distribution. Oh, hold on here. We have that third rule, which doesn't show up a lot, but it says if your sample size is at least 30, then your distribution of X bar will be normally distributed. So, darn, I guess I gotta do this again. So let's clear. And, oh dear, we can only go up to 25. But yeah, 25 is getting close. Let's see what happens. Oh boy, oh, we gotta wait a while here. It's sampling 25. And there we go, we got our first one. One more time. We're going to sample 25 from the population. Here they are, falling down. So yeah, this takes a while, doesn't it? Yeah, 25 is a lot slower. But, oh, there's 2. One more time. Pay very close attention. We are sampling from this population that I just made up. Doesn't look anything like a normal. And, oh my gosh, the sample doesn't look normal at all. But no, we don't care about that. We care about what's the distribution of X bar. Alrighty, so let's do 1 more. And there we go. Okay, well, all right, let's do 10,000. Not too bad. Oh, look at that, the one I was after before, 10.50. But again, it's very, very close to the population mean. Standard deviation a lot smaller, but oh, wait a minute, our sample size is 25, so now we're saying take this number and divide by the square root of 25. So yeah, we would expect a smaller standard deviation still. So, all right, I still want to see a little bit better here. So we just keep adding 100,000 at a time. We've got over 200,000, 210,000 plus the 3 I did originally. And oh my gosh, 10.51, 10.51. Standard deviation. I guess I'll work this out afterward. I don't want to wait while I pull out my calculator and find out what 8.27 divided by the square root of 25 is, but this looks pretty close. All right, so big deal. Why do we care? Why am I spending time on this? Because in reality, we don't know the population. We don't know what it looks like. We don't know the mean. How in the world are we going to do anything? Well, we know that our sample, when we take a single sample, is somewhere in this distribution, right? This is one of the 210,000 samples that could have taken. So, it's going to be pretty darn close, standard deviation is distance, pretty darn close from the population mean. Now, do I know what the population mean is from a single sample? No, unfortunately we can't do that. So why don't we just take 210,000 samples and then we could say the mean of our distribution is pretty close to the mean of the population. Doesn't that sound fun? Go forth and do 210,000 samples. Oh. Yeah. Tell you what, I'm going to pass on that. But we're going to see all these cool techniques of saying, what's the probability of getting our sample mean given that the population is what we hypothesize. We have a hypothesized mean, H sub 0, the null hypothesis, and we'll be able to give a probability. Now, what's the probability we're going to get way out here? This one? Oh, that's not very likely. But one that's very close to the mean has a high probability of occurring. So that's why we do this stuff. Well, aren't you impressed? Isn't that just the coolest thing? Now, as always, go ahead and respond. Let me know questions. And I'm talking to my computer camera. It's like, how you doing in there? So, let me know. If you got a question, by all means, tell me. All right?